Okay, this is going to be part two of the project, and this is going to be my own personal, which is going to be 5.1 through 5.4. Uh, my name is Brady Rogers, once again, going over the topic of the second law of the thermodynamics. Um, so, with the first slide, we got 5.1, which is relevant charge slash diagrams. Sorry about my name being in there. These were my own slides, so I wanted to mark them. But so for this, with the second law of thermodynamics, I said that many charts can show the description or depiction of the process of heat flow from a hot object to a cold object. With this specific diagram provided on the screen, as you can see to the right, it provides the viewer with an illustration that shows the core idea. Heat energy naturally flows from a hotter object to a colder one. As you can see, hot, whether it be a hot coffee cup or, a hot plate, it's going to transfer that heat over to the surface that it's sitting on, whether it be you're holding it or the table itself. I also said when a transfer like this occurs, entropy is also increased, meaning the energy becomes more spread out and less unstable. When it is all said and done, this process will be irreversible. So when that heat transfers over, something as simple as a coffee cup or a coffee mug, um, the heat that is moved from the coffee cup to the table itself, it's going to be irreversible. The heat can't transfer back up to the coffee unless the surface itself is a hot plate. So once this happens, it's irreversible. For the next slide, we got relevant formulas, constants explained. So I put two examples of formulas that are used. So for this one, the first one that you see, S equals Q divided by T. This is going to be basically the equation that relates back to the second law of thermodynamics because it shows how entropy changes when heat, which is going to be your Q. It's actually going to be your Q right here is transferred at a certain temperature. So you got your cold reservoir, which is going to be transferred to the refrigerator, which is going to be transferred to your hot reservoir. Sorry, it's cut off right here, but this is going to be your hot reservoir. So for the next one, you can see that it is W equals QH minus QC. This right here, as said in the recordings before this one, this is going to relate back to what can be used. The heat that is that made, which can be transverse back into work. So the equation listed above describes how a heat engine produces work. This is also related back to the second law because not all heat can be converted into work. Some energy must always be lost as heat to a colder area. And sorry, it's cut off. I think it did this because someone, I don't know if it was me that edited it wrong, but I mean, you can clearly see this is going to be the first step right here in the process, which is going to relate back to your first equation, and then the whole process of the cold going to the refrigerator. Heat's also going to be produced, which is going to be lost, and then some of that heat is going to be transferred back as work, which relates back to the second one, and it's going to be used, as a reoccurring cycle. So I just thought it was pretty cool how everything is kind of like a full circle in this this equation, these two equations. But as said before, some heat is always going to be calculated as a loss. But yeah. So for the next slide, we got 5.3 solving process. To solve problems using the second law, first the reader must identify the heat absorbed from the heat region and the heat released to the cold region. After that, subtraction is needed to cancel out the heat rejected. Sorry. After that, subtraction is needed to cancel out the rejected heat from the absorbed heat. So this is going to be the equation I explained earlier with the work equals QH minus QC. It's going to be your two reservoirs, or not reservoirs. This is going to be just the heat itself, which is found by subtracting each other to find the work. And if you really want to go further for the efficiency part, there's going to be another equation which you can use for temperature, and then your you know maximum efficiency, a maximum efficiency over the efficiency itself. Of course, you always want to do maximum efficiency to see exactly what is possible, but efficiency on a standard of not being perfect is just going to be your normal equation right here. So when a problem like this is solved, the answer will give us useful work produced by heat engine. So refrigerator basis is going to be kind of like your easiest to understand with the heat and cold on how it can be turned into something useful. So there's that one. Going on to the next 5.4 application to the second law. Several equations relate back to the second law, but with the one established and the two, I should have said, the slides before, it directly shows a real world system like an engine or a refrigerator. It explains how energy is transferred and why some of it is lost in the process. Like I said, the whole ideal behind the second law is the heat transfer and how we can turn that heat into something useful as quote unquote work. So moving on, it is important to understand the application because it also depicts limitations of energy efficiency in everyday technology. That being said, there's always going to be a loss and there's always going to be a gain. And the whole objective of this process is how much can we get out of a loss. So we started off with the loss being greater, with loss being greater than the win, which is what we can take and put back in to get something out. So it's an ongoing process of how we can further improve any type of machine or whatever it may be to have greater efficiency. And a picture of a little coffee mug, just kind of to give you a little bit more clear visual of obviously it's hot in the cup and it's moving to the fingers itself. Obviously the fingers are going to be colder than the coffee itself, so the heat is moving from the coffee mug to the fingers. I know it's not the refrigerator, but you get the gist on it. But yeah, so these are going to be my slides that I did, and thank you.